So next up is going to be Neal Parikh. Neal's going to talk about the basics of machine learning. A lot of really interesting concepts, but maybe the most interesting one that I think there's a general misunderstanding of linear and nonlinear models and why one may not be actually as important as you think it is. So Neal's going to talk about that, relative to other quantitative tools. Neal's the co-founder of SevenFifty, which is a New York City-based technology company. Really interesting. He received a PhD from Stanford in computer science, and previously worked at Goldman. So he's worked as an analyst in the industry, really deeply understands the problems. So not just a technology person at the end of the day, as well as has been a visiting lecturer in machine learning at Cornell Financial Engineering Manhattan across the river. So thank you for coming and doing this.
All right, so to get started, I'm basically going to talk about three different things. So first of all, what is machine learning and how does it relate to other terms you might have heard of, statistics, artificial intelligence, things like that. We'll look at a couple of examples of machine learning models, just what they look like on some data sets, and then some brief comments on some potential uses and some potential pitfalls in these kinds of methods. And I'll just preface this by saying I'm not totally sure of the exact level of the audience, so if you want to dive into a little bit more detail in the questions, I'll try to leave some time for questions at the end. I'm definitely happy to talk more about any of that. This should be skewed pretty basic, no math today. So we'll just set the stage by giving a couple of examples, and these aren't finance examples, but they should hopefully just get your mind jogging. So this is an example I call Finding Spy Planes. So BuzzFeed News published an article about a year ago, August 2017. The title was U.S. federal agents flew a secret spy plane to hunt drug cartel leaders in Mexico. So these journalists had basically dug up a bunch of weird planes flying over the domestic United States and over Mexico. So military contractors flying over the Bay Area, secret U.S. Marshals planes hunting drug cartel kingpins with the Mexican government, some Air Force Special Operations planes, the Palm Beach County Sheriff's Office was doing something, and they published an article about this. And you might wonder how exactly they came across this information, and it might be leaks or other types of journalistic practices that they use. But actually what happened was that they used a machine learning model. So, and they wrote an article about this. They say they trained a computer to search for hidden spy planes, and this is what they found. And they kind of go through their process. And the sort of cartoon recipe for what they did was they pulled a publicly available data set. It's obviously not intended for this purpose. It was not to find secret government spy planes. They trained a simple machine learning model, 1 page of code, okay? And then they validated it. So they did journalism in this case. So they followed up by calling the Palm Beach County Sheriff's Office and confirming with them using their sort of traditional non-computer-based journalistic methods. So there's a sort of a human in the loop, and they were using this as a tool to complement their existing tools. And to get a little bit more precise, what they did was, there's a website called flightradar24.com, and it gets data from air traffic control towers. They pulled 4 months of data. This is publicly available data. There's different amounts of information available on the different planes, and FBI planes, for example, are missing a bunch of different markings. They're not flagged as such. They're owned by some shell corporation that isn't identified, and so on and so forth. They then extracted quote-unquote features, so different measurements or characteristics of the raw data, which includes the flight path. In this case, turning rates, speeds, altitudes, the manufacturer of the plane, and so on, maybe a couple dozen of these things. They then trained a type of machine learning model called a binary classifier. This is a category model, not a specific model, to distinguish between spy planes and not spy planes. Okay, so it's called a binary classifier because it classifies the input. The input data is stuff about the flight path, and it's binary because there's two options, yes or no. Okay, and we'll see these a bunch of times through the rest of the presentation. And then they do the validation. That's the do journalism part. And this example kind of has in it all of the characteristics of the brave new world of machine learning, which is that a couple of things I might highlight about it are the following. So number one, there are a ton of data sets out there. So there are a lot of publicly and semi-publicly available data sets. And a lot of them contain a lot of information that they were not intentionally, that they aren't originally intended for. So this is not a spy plane data set. It's just a generic flight data set. And these journalists had a brainwave to use it to pull out this additional information. There's essentially a huge amount of information in these data sets that's written in invisible ink. And the way to see what's written in there is using statistics and machine learning methods. A second thing is that this does not have to be very complicated. There are very, very powerful models that can be used on these kinds of methods. These are not some research grade models. These are canned packages that someone used in R. The person had to know enough to know that this type of model is appropriate for this type of problem. That's very important. So you don't want to get into the sort of buzzword bingo of just download some random thing and throw it at your problem. Definitely want to avoid that. But you're also not reinventing the wheel every single time. So again, this was around a page of code. And then the third thing is that sometimes people talk about AI and machine learning as replacing jobs or completely replacing a person. And in many cases, that's not the case. It can be sort of a power tool that's used to complement the existing journalistic process. These are journalists that did this, and they still had to do a number of other steps that were traditional in using the output of the model. What the model spit out in this case was a ranked list of what it thought were most likely to be spy planes, and then they called people up and double-checked all of this, and it ended up being quite accurate. The last thing I might say is a lot of people are using this now, so if you don't think that you might need to use these types of things, somewhere BuzzFeed News is using this to write blog posts and journalistic articles, so it's disseminated out pretty far. A couple of other examples, I'm not going to go through all of these, but this is just to sort of emphasize the range of applications. Some of these are maybe slightly more unusual applications from familiar players, Adobe and Amazon. But a couple I'll highlight. One is Cheesecake Factory. So Cheesecake Factory uses machine learning methods to predict orders. Basically, they use it for purchasing. And they waste basically no food. They waste like 1% of the food that they order. And if you've ever been to the Cheesecake Factory, you know how amazing that is, because it's an absurdly large menu with almost no overlap in the ingredients across the 300, 400 items that they sell there. So you need to be pretty accurate at predicting aggregate demand in their stores, and it's also perishable items. You can't just let stuff sit around. So this is one example. C-SPAN does not have a reputation for being a high-flying tech operation. But they use computer vision models to automatically caption which politician or public figure is on screen at a given time. Third example, which is a little bit more modern and AI-ish, is something called HireView. And this is one of a number of companies that does this kind of thing. Instead of interviewing for a job with a person, you interview with a video camera. And the camera will screen a bunch of things about facial expression, sentiment, and any number of other things to try to predict. It's another binary classifier, basically. Good candidate, bad candidate. Do I pass this person on to the next stage in the process? And this, is debatably a good thing, and that people may have a number of concerns about this, which I'm not going to draw on here. But there's many, many other examples in all kinds of different sectors. All right, one last one before we get on. And this is a kind of, this is a modern example. This is going on this month, and it's in medicine. So this is a sort of high-impact, high-risk kind of deployment. So there's a condition called sepsis. Sepsis is the third leading cause of death in the United States. Hospitals actually often miss this. They often miss the early warning signs, and a very large number of people die from this. So a number of university hospitals it is not a well understood enough medical condition to be able to design very simple systems to automatically detect this. So people are using machine learning systems basically to produce early warning signals that a patient may be about to get sick with sepsis and then get treated before that becomes a fatal condition. So Duke, Johns Hopkins, some others are deploying machine learning systems, some this month, one called Sepsis Watch, for this kind of detection. So in this case, the Duke system's trained to take 50,000 patient records, over 32 million data points overall, all kinds of different variables, vital signs, lab tests, and so on. And then basically that when the machine is running live, when the system is running live, it's pulling patient data every 5 minutes, it's making a new prediction, and just like the BuzzFeed example, if it flags the patient as being at risk, calls a nurse. It doesn't automatically treat the patient necessarily. And then if the nurse can decide whether to agree or disagree with the warning, if the nurse agrees, then the system walks the nurse through a checklist of follow-up items that should take place. So this again has some interesting things about it in terms of how the types of ways people are using machine learning systems. There are different binary classifiers, both this one and the BuzzFeed one. For those who are interested, I think in the first case they used a random forest. In this case, it's some kind of deep learning system, but it doesn't really matter. I mean, the sort of the high-level structure of it is the same, and it's being used in all kinds of ways, often with a human in the loop. Okay, so this just gives some flavor for what we're talking about. Now let's talk about what is machine learning and what isn't it, because I think there's a lot of confusion about it. But the main thing I kind of want to leave you with is that machine learning is not a thing that is sort of totally different from statistics. So statements like, should we use statistics or should we use machine learning are sort of grammatically nonsensical. This isn't the way to think about it, and really machine learning is just a set of methods on the same spectrum as things that you may be familiar with and using already. And it's just a question of which tool is appropriate for the task. It's like saying, should you use a hammer or a screwdriver or a power drill? Well, it depends on what you're building, and just sort of use appropriately. So there's no precise technical definition of machine learning. The usage has sort of evolved over time. Historically, it's emerged as a subdiscipline of artificial intelligence research. And I'll talk a little bit more about the history of AI in a minute. But that's actually a very important historical thing to be aware of, because it accounts for a lot of the terminology that might seem quite weird in machine learning. That why would you call it these kinds of things? So specifically, what it is basically is that it is the intersection of computer science and statistics, which before were two fields, now are heavily overlapping. And it's, if you wanted to summarize it in a sentence, it is computationally tractable algorithms that learn from data. The learning from data part is the statistics part. The computationally tractable part is the computer science part. And there's a sort of, you can make this more technically precise, which I won't do here. And again, it comes out of AI, but now it's used in a huge variety of other domains. And to get a little bit more precise, what it's about is how to build learning procedures. So how do you use historical data to build a prediction rule, where a prediction rule is an algorithm that maps inputs to some kind of response or output. So in the BuzzFeed example, the input is all this stuff about a flight, manufacturer, altitude, and so on. And then the output is spy plane, not spy plane. It could be a much more sophisticated or complicated kind of response. It could be many categories. It could be a given number. It could be a whole kind of structure, like a translation of a sentence from English to French. But it's basically mapping some inputs to outputs, and it learns how to do that from some kind of data. And the sharp focus in machine learning is on making predictions. Can you use this to predict new data that you have not seen well? It's not about explaining the existing data that you have seen, which was some of the focus of more classical statistics. So it's not so much that machine learning is sort of not statistics, but it places the emphasis much more strongly on prediction specifically. And informally, at this point, it's basically interchangeable with the terms AI, and interchangeable with the term modern statistical prediction. So there's plenty of people in statistics departments who are doing machine learning, old statistical models that predate even the term machine learning. You should think of as machine learning models. It's sort of a way of modeling things. It's really this whole process. It's not a specific set of models. So Sepsis Watch, you might say, is an AI. It's not an AI in the sci-fi kind of C3PO sense. It has a very limited purpose. But because of the historical development of the field of machine learning, these are basically interchangeable terms. I mean, if you're doing sort of academic work in this area, there may be some purpose in making a distinction, but otherwise people are not so precise, and there's no need to make these kinds of distinctions. Okay, you could call the BuzzFeed thing an AI too, and you're not using that as an ongoing system really, but that would be fine. But this is all modern statistical prediction. Okay. So just a little bit about the history. So AI starts in the 1950s. That's when the term was coined. These things called the Dartmouth conferences. Some of the early work was on game playing, chess and checkers, stuff like this. There was a lot of work on the philosophical foundations of AI, philosophy of mind, cognitive science, stuff like that. There was a bunch of bumbling around in the 70s and 80s with tools that were mostly based on the mathematical foundation of formal logic, okay, and neural networks. Both these systems, all of these ideas basically failed, and they led to two different AI winters, they're called, which was when all of the funding for the field dried up because the stuff was just not working. Then you come to this big watershed moment, starting in the 1990s roughly, is when the probabilistic revolution takes place, and people start using probability and statistics to attack these kinds of AI tasks. And this is when machine learning essentially merges with statistics. It becomes the same field, more or less. There is a number of different sets of models that were pioneered in this time: graphical models, Bayesian networks, kernel methods, and so on. In the 2000s, there was more importing of traditional areas of applied math, so optimization theory, which is the basis for portfolio optimization and stuff like that. So a lot of work on convex optimization started getting imported in the 2000s, and in the 2010s, it's mostly been dominated by a new set of work in an area called deep learning. But basically, below this bar is when machine learning merged with the rest of the mathematical sciences and the mathematical community, and started using standard terminology and tools, and started acknowledging the overlap in the problems that everyone was talking about. That, oh, this is actually a thing people in stats have been talking about for a while. We need to develop new methods because the data we're talking about is different, the tasks we're talking about is different, other things like that. But started using more terminology from statistics and optimization and so on. But because of the origins of the field in cognitive science, neuroscience, philosophy, and so on, there's a bunch of residual terminology that comes from that era of machine learning that may seem sort of very evocative, where the computer is learning something, but it really corresponds to a relatively dry mathematical term from other fields. And this is sort of half a joke and half a real thing, but people have even come up with sort of translation dictionary between statistics and computer science / machine learning. So what's called learning in machine learning is parameter estimation, model fitting, data fitting. More boring, but it's the same thing. What's called supervised learning in machine learning. These are regression and classification problems in statistics. The reason for the use of the word supervision is, again, from this sort of the top half of the previous slide, when people were trying to come up with heuristic methods by analogy with a teacher supervising a student and so on and so forth. But it was only decades later that people unified it with standard statistical terminology. There's a bunch of these other examples. Sometimes people add a last one, which is average grant size, and it says like $100,000, $10 million over here. But that's another story. Okay, and you'll see the computer science terms are kind of a mishmash between these cognitive sciencey things, supervision, learning, training, stuff like that, and things from engineering, inputs, outputs, very sort of mechanical kind of terminology. Okay, but it's all really the same stuff. All right, so let's look at a couple of models now. This is the first machine learning model. Okay, so it starts a huge disappointment to all of you. So this is linear regression in one dimension or two dimensions, however you want to call it. We have an input, and we're predicting a continuous output. So there's a number that we're trying to predict. So the inputs are on the x-axis, the outputs are on the y-axis. You dump in the green points into a little machine, turn a crank, it spits out the blue line, and when you see a new point, you look up how high it is on the line. It will tell you, the input is how far it goes horizontally, and then you look how vertical you want to be on the blue line. That is your prediction. Okay, that's it. And the way you judge whether or not that's a good model is you try it out, roughly speaking, and you see how good a job does it do at predicting the height of the new points that you haven't seen. That's the machine learning part. It's using the model in that way, as opposed to, for example, an R-squared or a goodness of fit test. All right. So now we'll look at a supposedly nonlinear model, but it's sort of, it is and it isn't. So this is an autoregressive time series. So what we're looking at here is the x-axis or the t-axis is time. So this is hourly measurements at LAX airport. Y-axis is temperature in degrees Fahrenheit. Okay, so we're trying to fit some model of temperature variation by hour. And it has this very nonlinear looking shape. It goes up and down as you would expect according to different times of day and things like that. It actually turns out that you can fit this curve using this. So if you only have one piece of computer code or one button you can push, and what the button does is you stick in a bunch of points and it gives you out this blue line. With that button, you can produce this blue line here. So this is why this whole notion of what exactly do you mean by linear or nonlinear is a little bit more subtle and maybe a bit of a red herring. And the way you do that is by massaging the input. By altering the way that you're feeding the data into that model, you can produce this graph. There is an underlying linearity in this, basically. So I'll leave it at that for for this talk. But you can fit this with a linear estimation procedure, and that's the case for many plots like this that look highly nonlinear. Here are some other ones. So this is called polynomial regression sometimes. So a polynomial, smooth wiggly curve, and the degree of the polynomial is how many times it wiggles, right? So a quadratic or a degree 2 polynomial wiggles once, it's a bowl. A cubic can wiggle twice, right? So this is a bunch of green points again, and now we've fit 4 models to it. One is a degree 2, degree 6, 10, and 15. So the degree is going up, more wiggles, and increasingly wiggly curves. This also you can fit using a linear regression model. It's linear regression, basically, with modified input data or modified features. So is this linear, is this not linear? It depends a little bit on what you're talking about. The other question that now immediately arises, which is really at the heart of machine learning, is, well, now how do you know which one of these to pick, right? Which is a task called model selection. Now you have too many models. You've got all these 4 different things. So just on a purely intuitive basis, you can kind of see what's going on here. So the quadratic one, the degree 2 one in the top left, it seems a little bit too simple. So there's a sort of uptick at the end where the points start going further up to the right, and there's a little bit more complexity somewhere in the middle that it doesn't seem to be picking up. Meanwhile, if you go to the degree 15 one, on the bottom right, it's kind of going all over the place, and it's not really clear that all of that is for a good reason. It may just be picking up, intuitively noise in the data. I'm not going to make any of these terms precise, but you can kind of see roughly what I'm talking about just from the picture. So it seems like probably you would want one of the two in the middle, the degree 6 or the degree 10. And the reason for that is you want to do a good job matching the data that you have seen. You want to capture these green points well. So you don't want to underfit the data. So this degree 2-1 is underfit. It's too simple. And a degree 1, which would be a straight line, would be terrible. That would be way too underfit. But you also don't want to overfit, which is the degree 15 one, because what's going to happen is all you care about is the points you haven't yet seen. And if you make it wiggle around too much, it's actually going to perform worse for the new points than one of these simpler models. So there's a Goldilocks problem here where you want just the right level of model complexity. You don't want to go too high, but you also don't want to go too low. Both of them are bad. And the core of machine learning in some sense is how to select which of these 4 to use. And there's an automatic procedure essentially that will select the right degree. And you select the right degree, roughly speaking, by trying it out and seeing which one does better on data you haven't seen. And that's called model selection. So this picture is just a useful one to keep in mind. Without even making the terms precise, you can kind of see what's going on. And again, these are all linear, these squares fits. Now we'll look at something else. This is squarely a machine learning model. This is from the 1990s. There's no kind of debate over whether it's machine learning or not. It's something called a support vector machine. This is a binary classifier. So the task is, I'm going to give you a point, you tell me yes or no. Okay, so we've got all these points. Some of them are blue points, some of them are purple points, and we want to distinguish between the blue and purple points. We want to select this line on the right, and then what you're going to do when you get a new point is you literally just check which side of the line you're on. If you're above the line, you predict blue. If you're below the line, you predict purple. And as you can see on the left, I'm not going to go through the details here, but basically there's a lot of different lines you might draw, to distinguish between these two groups. The support vector machine is a particular way of choosing a good line that will generalize well to points you have not seen. There's a lot of math behind that. But you'll notice here too, this is linear. This is a linear fit. This is a machine learning model from the 90s, not from like Gauss, which is where linear regression comes from. This is a machine learning model, and it's giving you a linear fit. So this whole notion that sort of statistics is linear, machine learning is not linear, this is sort of not the right kind of distinction. Okay, and just like you can soup up the linear regression model to do this time series thing, the polynomial regression thing, any number of other types of fits, this can be souped up too. So these are nonlinear support vector machines. These are obviously more used in practice than linear support vector machines. Main reason that you want the sort of greater machinery is to be able to fit these more complicated kinds of situations. But look at this case. So now the purple points are in between two groups of the blue points. It's sort of obvious you can't just draw a line to separate the groups. You just have to have a more complicated model. You need some equivalent of the wigglier line. And here are two examples of different nonlinear support vector machines with these boundaries. So in this one on the left, something called a polynomial kernel. It is able to drop two lines and split it up that way. So if you're either on the lower left or the top right, you're blue, otherwise you're purple. And in this one on the right, you're dropping this sort of circle-ish shape around the purple points. Everything inside is purple, everything outside is blue. And there's all kinds of math and this and that that goes into it, but you you can clearly see that you need some model like this in order to capture data with this kind of structure and complexity. Okay, these actually are just souped up linear models in a certain sense, just as the polynomial ones are souped up linear regression models. But you can do very sophisticated stuff with things like this. Okay, so one kind of random example to show you where you might, things where they've used support vector machines in practice, and also to show you sort of how far you can push what seem to be sort of toy models where all you're doing is spitting out yes or no answers. So this is a problem called splice site recognition. It's a bioinformatics problem. So you have DNA sequences, they go through this transcription translation process and spit out proteins at the end. Proteins do the work of the cell and so on. So there's lots of cases where you want to analyze subsequences of DNA. So this is sequential data. So the order that you're reading it in matters. It's not, just random points. And basically, the DNA sequence is subdivided into two types. There's introns and there's exons. The introns get sliced out in the middle of the process, so they never end up in the protein. The exons are the ones that actually get expressed and are in the protein. So you want to know which part is the intron, which is sort of garbage sequences, which part is the exon. All of the introns are sort of bordered by the same nucleotide subsequences, these GTs and AGs. So you can use that as a pre-processing thing, that these are at least some candidates. But most of those things don't actually turn out to be real splice sites where the DNA gets cut. So you might do this with machine learning. This is not a biologically well understood enough thing in order to have a purely biological model. You have to use some kind of statistics to attack something like this. So what you do is you extract the candidates and then you run a binary classifier on it. These ones are, and it'll spit out, just like it says yes or no. This is a splice site, this is not a splice site. In this case, they used a support vector machine. So you end up with these points in space. The blue ones are, I'll just make it up, the blue ones are splice sites, the red ones are not splice sites. The different axes are different measurements about the nucleotide data. And now you're just trying to figure out, drop a line in between that distinguishes the two. And maybe you can do it with just a line, maybe you need these curvy decision boundaries. So you've got a straight line here, a linear one, and then there's a polynomial kernel of degree 2, so it's a sort of bowl-shaped quadratic thing, and then you've got one of degree 5, which is much more wiggly. And intuitively, you can kind of think through which one kind of feels the most generalizable, but of course in practice, you'd use an automated procedure to select which of these has the best predictive performance. And then you can validate it, just as you do journalism at the end of the BuzzFeed example. You can sort of do some biology after these predictions are given and verify that these really are splice sites. And they have ways of doing that. So even these very exotic examples that you read about sometimes in the paper or whatever, it's really just creative uses of quite simple machine learning models sometimes. This is not such a simple model, actually, in this case. They use some custom bio stuff in this support vector machine, but it's not so complicated either. And creative uses of it, and putting a bunch of little sort of Lego blocks together. But this is very much on the same spectrum as all of the other examples that we talked about, including something as sort of babyish as linear regression. Okay, so we'll just close with some uses and pitfalls. So some uses are obviously, you can explore all kinds of different data sets in a much more effective way, especially things that involve text, images, satellite images or not, video, other stuff like this. You're basically immediately in machine learning land. The other is actually internal operations, and hopefully some of these sort of unrelated examples that I threw up, like early warning signs for sepsis, jog some ideas in your head that There's all kinds of things in anomaly detection, internal processes, data processing, data quality, market condition monitoring, and so on, that you may use these kinds of methods for. The third one is, of course, actual trading signals. I put this third just because it's obviously a lot of what people do with machine learning at some types of funds, but it's far from the only use case for these kinds of methods. You don't have to go sort of 0 to 100. There's a lot of good uses for these purely internally. And these are just a couple of examples just to jog your thinking. There's not a comprehensive list. For pitfalls, one is that, of course, you need an appropriate team and appropriate workflows, which may be different from the people you have. It's very important with these kinds of methods to have people that have appropriate theoretical understanding of what they're doing, because the methods cannot just be plotted. It's not so easy to understand where a model may be going right or wrong, and having some theoretical understanding of the model, actually one of the biggest uses of theory in something like machine learning isn't debugging. It's being able to sanity check that something is doing what it's supposed to. Also, workflows. So just as in the previous talk, there was the example of non-stationarity. Does the model keep working? It's common, even in things other than finance, to make sure that does the model need to be retrained, and having human processes like weekly model diagnostic meetings, and also automated processes. What are the things that you're checking from the model to keep an eye on something potentially going wrong as part of the sort of portfolio management process. A second one is roughly something that's called sort of algorithmic bias and ethics. It's not really ethics in this context, but improper use of data and insufficient care in training these models can cause the models to misbehave in odd ways. So you can quite easily end up with like like a racist computer vision system because of the data that was used to train it. It's very common. There was a story in the news in the last week that Amazon had to pull an AI that they trained for screening applicants for hiring because it was gender biased against women. Probably what it was picking up in that case is that Amazon was gender biased before, and the data that they fed into it was gender biased. But it's not always so simple. It's not just that you feed in biased data. The statistics can pick up on weird structure in the data. So sometimes there's an ethical component, but sometimes it's just misbehavior. And the last one, this sort of goes back to what I was talking about, the source of the terminology. The terminologies are very evocative. Sometimes it's neural, the computer is learning. People like to talk about HAL 9000 and Terminator and all this stuff. It's just a statistical model, and so wrongly anthropomorphizing it can be very dangerous and misleading and kind of counterproductive. I say wrongly because sometimes just for building intuition, because the models are so complicated, putting yourself in the model's position can be sort of a useful way to think through what's going on. That the model likes this type of data, doesn't like that type of data, but it's important to just keep in mind that's a linguistic trick, and sort of for building intuition, it's not anything deeper in what these methods are doing. Okay, so I'll stop there and kick it over to questions. If there's no questions, I have one other example just in case, but I'll stop there. Thanks a lot.
Can we do some of the math there?
I mean, I don't have any math for you today. Is there some specific math you wanted to do?
No, I have some background in math, so I was hoping that like when you were doing the quadratics and stuff like that.
I mean, the regression one or this thing?
No, like this, not this thing. The stuff before, or is it like I have some questions about. So is 6 or 10 the right one, and how do you figure that out? And then how do we think about the actual formulas for the regressions that this would spit out? What does the 10-degree least square even look like?
Oh, well, it looks exactly this. The formula is actually exactly the same. So if you have, that's kind of the point. So you're still solving a quadratic problem. These are all, every one of these models is a convex optimization problem. Also, so you could just solve these. There's no heuristics or anything like that. These all have closed form solutions. You're just solving the normal equations. What you're doing is you're adding more features. You add interaction variables essentially, and you will end up with a nonlinear fit. So if your raw data is x, and you do a linear regression on x squared, you will end up with the degree 2 thing. That's really all it is.
What about the degree 6?
Same thing. You just add 6-degree interaction variables.
And then if you wanted to put, so did you see the guy that did the hand-drawn example earlier from Estimize?
Yes.
So he had this scenario where like the kind of the cutting edge now back to the multi-factor model is you take 5 or 6 degree 6 models and put them together in some kind of 3D cube. That was a nice drawing.
Well,
that cube, like from a math perspective, makes no sense with this one. It was just for visualization.
So how do I?
So these are very high dimensional models.
You can't fit, like it's very hard to draw a high dimensional model.
Well, you can't. So these are so. No. So for instance, if you're doing linear regression, let's just take linear regression, and you've got 30 inputs that you're regressing on, you're working in a 30-dimensional space. You can't plot that regression either. So I'm not sure.
And it's just a black box in the computer that you can't really get any.
You can get lots of information about it. You just can't plot it. Because think about if I have I'm trying to predict income from height, weight, and age. Okay, so now there's 3 inputs. You can't plot that. You can fit a linear regression model to it. You can fit that model in like a microsecond or something on a computer. It's one line of code in MATLAB, but you can't actually plot that relationship because it's 3 input variables and 1 output variable. So it's nothing to do with these very fancy machine learning things. It's actually just this is not actually harder to plot or any more mysterious than doing a regular linear regression with like 20 variables or something like that. It's increasing the number of variables. So the irony is actually that, I mean, you're asking for the formula. These all have the same formula. So does the autoregressive time series one. This one actually might make it a little bit clearer. So the reason why this one is linear is that it's a linear fit to the previous set of data points. So basically you copied a lot of the input data, which is a time series. So you predict like 11 a.m. from the measurements, which is a linear fit on the temperature measurements from 6 a.m. to 10 a.m. And then you predict noon from 7 a.m. to 11 a.m. and so on and so forth. So it's a time series. It's a linear regression. You can design an X matrix and just do backslash in MATLAB and get this thing out. It's just that you copied the data in a careful way. But there's a lot of variables. I mean, there's a lot of variables that you're putting in there, which is fine. But again, you're not going to be able to plot any of it in the way you're talking about. Make sense? Yeah.
Yeah, I was curious, does the concept of statistical significance change, evolve, become reduced in a machine learning context?
That's a really good question. In many cases, it changes. It changes because it depends on the type of model that you're talking about. It may be the case that, again, because the focus is on prediction. So that's a very big difference culturally in the way you're using even some linear model versus some sort of social science purpose where part of what you want to get out of it is which of the variables are important. In these cases, we didn't really care. So the short answer is yes, it depends on the type of model, and sometimes that's one of the things that will dictate which type of machine learning model you use and how you use it, that that's part of what you want to figure out. So just to give one example, a very, to get some math and buzzwords in and stuff. So one thing that's become very popular is the use of L1 penalties, L1 regularization. The idea here is you're doing a regression problem. You've got like 100 million variables though, and you're trying to predict, is this tumor cancerous or not? And the reason you have 100 million measurements is because the medical device is so sensitive. Now you don't actually think all 100 million variables are predictive of the output. The problem is you don't know which ones are or aren't. Maybe only 50 of them are. So what you do is you solve a particular variant of this regression problem that simultaneously does the linear fit and selects, so it'll zero out all but 50 of those variables. In those cases, those 50 do have more explanatory power, and those follow-up tests you can do to test certain things about the significance. But for example, deep learning models, that's just not what they're used for, and people are working on those kinds of things. But it is something that will dictate which models you use, which is another value of the theory, that you would just know before even fitting anything, you can answer this type of question about this model and not about that model. That's a really good question. Okay.